Now that the Edge Manager is installed, we'll focus next on onboarding and managing our delivery drone edge devices. Let's start with part 2 of this demo. We'll start with building device image and deploying it to the device. We'll then onboard the device to Edge Manager, which will add the device to the fleet. Once added, we can then start managing the device. So let's have a look at the build process. The first step is creating an image mode bootc image. We build the bootc image using standard Podman tooling like Podman and a container file. Once the container image is built, we use the bootc image builder to convert it into a bootable disk format, such as ISO or Q2. In most real-world scenarios, this image would be written to a removable media and installed on physical edge hardware. In this demo, we'll use an OpenShift virtualization virtual machine to represent the delivery drone. So we'll create a Q2 image. To onboard the device, Edge Manager requires three things. The Edge Manager agent. This is the device agent that uses a pull-based architecture to retrieve configuration and updates, which is well suited for edge environments where inbound connectivity may be limited. It needs an image mode image. In this demo, we'll build our image mode using the container file. And number three, it needs an enrollment configuration. This configuration file contains the information required for the device to enroll and authenticate with the Edge Manager. Let's take a look at the container file. As you notice that the container file copies the enrollment configuration file into the image. Let's get that using Edge Manager CLI commands. Let's log into the Edge Manager and create a certificate request. Now we have the config file and the certificates for the Edge device to properly enroll and authenticate with the Edge Manager. So how does the agent know which endpoint to contact when the drone device is powered on? It's all written in the config.yaml. The server address shown above identifies the Edge Manager API endpoints used during device enrollment. Port 7443 corresponds to the Edge Manager API service. When the drone virtual machine is powered on, the Edge Manager agent reads this value from the config.yaml and uses it to send its initial enrollment request. By default, the Edge Manager agent on the device checks in with the Edge Manager backend service every 60 seconds, but we can speed it up for this lab. Now let's build the image next using podman build command. The image is successfully built, so let's verify that the image mode container image exists locally. At this point, the image resides locally on the virtual machine. We could push this image to a container registry, but for this demo, we'll convert the image into a disk format that can be utilized by our drone virtual machine. Since our drone device is represented by an OpenShift virtualization virtual machine, we'll convert the image to the Q2 disk format. When we installed the Edge Manager on RHEL, it was deployed as a set of Podman cordlets, which are systemd managed containers running directly on the Edge Manager host. Each Edge Manager microservice is defined as a separate systemd unit, which makes the platform modular and easier to inspect, operate, and troubleshoot. Let's inspect the Podman cordlet services installed on the system. The services within init suffix run once at the startup to perform initialization tasks. The services without the init suffix remain running and provide the ongoing Edge Manager functionality. Let's filter on the init services and then filter on the long-running Edge Manager services. These running services collectively form the active Edge Manager control plane, responsible for API request handling, background reconciliation, authentication, and device communication. API service sits at the heart of Edge Manager, acting as the primary coordination point between clients, workers, observability components, and backend services. The Edge Manager CLI is already pre-installed in our lab VM. If desired, users can access the CLI download directly from the web UI. An Edge Manager fleet is a logical grouping of devices that share a common desired state and management policies. Fleets simplify large-scale operations by allowing the administrators to define a single fleet specification that applies consistently across all devices in the group. This specification can include applications, host configurations, and OS image references, ensuring predictable behavior and updates across the fleet. A device can belong to at most one fleet at a time. This design avoids configuration conflicts and ensures each device has a single authoritative source of truth for its desired state. Let's create a fleet. Fleets do not explicitly add devices. Instead, a fleet defines a device selector, and any device whose label matches that device selector is automatically added to the fleet. And for the demo, we're going to add the device selector as fleet equals lab. You can also utilize multiple device selector label matches. This is the bootc system image we just built. By specifying a system image at the fleet level, Edge Manager enforces which OS image must run on all devices that join this fleet. If a different bootc image was specified here and made available via an OCI registry, Edge Manager would automatically trigger an OS image replacement when a device joins the fleet. This makes fleet-level OS control a powerful capability for enforcing consistency and performing controlled OS updates across Edge devices. This section denotes the configurations that will get written to any device that is a member of this fleet. We're going to use an inline configuration now that is defined directly in the UI. And we also have an option of defining a Git-based configuration. This inline configuration will write a message of the day file to the specified location. Edge Manager will instruct the drone device to pull this application container from an OCI registry when the device joins this fleet. Because this application is defined at the fleet level, it will be deployed to any device whose labels match the fleet's device selector. Let's track the system time service on any device that joins the fleet. When a device joins this fleet, a new desired state for the device will be created, and Edge Manager will instruct the device to move itself to that desired state. But if there are thousands of devices in a single fleet, how will those desired state updates be applied? By default, we use basic configurations, which means that all devices will receive updates as soon as they are available. This may not be desirable when more granular control over update timing and rollout behavior is required. So we have the ability to specify advanced configuration update options here. For this demo, we'll just use basic configurations. Now that the fleet is created, we are ready to accept devices to it. Let's set up our drone edge device first. With physical edge devices, we would be using an image burning utility to write this to removable storage media that can then be inserted into the device. In our lab environment, we are working with OpenShift virtualization VMs, so we'll expose the disk image to the OCP word catalog when we create our drone virtual machine. I'm skipping over the details of that part in the interest of time, but you can see here that the drone VM is now imported as a data volume in OpenShift. The VM is running, so let's look at the VM's console. You can observe that an enrollment QR code is present, which the field techs could scan to initiate the Edge Manager enrollment approval flow. In our demo, however, we will approve the device in the Edge Manager UI. The agent on the device checks in with Edge Manager backend service every 60 seconds, which we updated to 10 seconds. Each check-in reports device information and status back to the Edge Manager. Notice under the system status, the device reports that it is not currently running any containerized applications. It's in an online state and reports an upgrade status of up to date. Note that the agent also reports CPU, disk, and memory pressures for the device. Note the system image that is currently running on the device. This is the image that we built previously and used for this drone virtual machine. It is also the image we configured earlier within our drone fleet as the desired OS image state. We also get terminal access. This terminal session may look like an SSH connection, but it is not one. Instead of connecting directly to the device over SSH, Red Hat Edge Manager provides terminal access using MTLS encrypted gRPC tunnels over HTTPS. We can see the RHEL version. Notice there is no message of the day. This is because we set up the MOTD as part of the fleet configuration but this device has not joined the feed yet. We can also look at any events being reported on the device. So we have successfully onboarded the device to the Edge Manager. And in the last part of the demo, we'll start managing the device.